Hi there, I'm Christopher Worse and welcome back to Homework 4 for Material Energy Balance. This video is going over Part 2, which asks us to code, solve, and plot the time-dependent concentration and temperature profiles for the CSTR with the given step changes in coolant temperature. Now I have to the side of me our equations that we found. I'll be using those to code out and to solve it, along with solve IVP from Scientific Python. So, in example 2.5 on the screen, it says two cases are simulated, one based on increased cooling by changing the cooling temperature from 300 Kelvin to 290 Kelvin, and one reducing the cooling rate by increasing the cooling temperature from 300 Kelvin to 305 Kelvin. Now, as I mentioned earlier, we have all of our values down here, and we will be inputting those into our collaboratory script. So, I have a blank collaboratory script here, and the first thing we're going to do is to import numerical Python as NP. We also need to import something from Scientific Python, so it's from SciPy import solve IVP, solve initial value problem. We'll be using that script to solve our actual differential equations and to get the values and to plot them. Now, plotting, we need from plotly underscore subplots import make subplot. We also need to import plotly.io as PO, and then we need po.templates default to equal plotly underscore dark. Shift enter should run it. It's connecting. Fingers crossed the nope. From SciPy. Oh, not SciPy. SciPy.integrate. There we go. Had to be more specific. Plotly dot. Oh. Cannot import make. There. Little errors here and there, syntax. All right. So now that we have all of our syntax ready, we can pull up our variables, and it's going to be a lot of switching back and forth, so I'm actually going to pull this over to a second monitor to make things easier, and then I'll pull it back once I'm done. So Q is going to be equal to 100 liters per minute, CA underscore in is going to be equal to 1 mole per liter, and these pound symbols or hashtags just make it so it's irrelevant just for labeling purposes. The initial temperature, initial TI, just going to call it TI, is equal to 350 Kelvin. It's actually TN. And we've got our volume. Volume is equal to 100 liters. Density, call it rho, is equal to 1,000 grams per liter. C is going to be equal to 0.239. That is joules per gram times Kelvin. HR is equal to 5E4 joules per mole. Then ER is going to be equal to 8,750 Kelvin. K naught is going to be equal to 7.2 E10 that is minutes to the -1. Inverse minutes, UA is going to be equal to 5E4, 5 times 10 to the 4th, joules per minute Kelvin. Oh, let me mark that off. TC is going to be equal to 300 Kelvin. CA is going to be equal to 0.5 mole per liter, and these are actually at 0. So I'm going to TC naught, CA naught, then T naught is going to be equal to 350 Kelvin. And that is just our initial variables, initial setup. So with that, we're going to have our right-hand side. So we're going to be defining an equation. So define right-hand side, and we want to enter time, because solve IVP requires time to be a first variable, as well as vec. Vector, again, is just going to be our every other variable. Speaking of, I need to put, because most of these, if not all of them, are integers, and I don't want them to be, I'm going to have to put dots here. Good. Okay, should be good. Enter, make sure that's there. Okay, so first we're going to be unpacking our vector of variables. So we have Ca, our concentration of A, as well as T is equal to vec. Those are our guesses that we'll be using later, and then we want to, as we wrote earlier, remember K is an equation. K is equal to K naught. I want to make sure that that's correct. Yep. Times NP numpy dot exponent times E R divided by, and I believe it's negative ER. Yes, ER divided by T. Yes, okay. Now we can, with CA and T, now we can return our wanted variable, our wanted equations. So I'm going to start with our equation for the change in the concentration of A. So that's going to be Q divided by V times CA in minus CA minus volume times K times CA. We also have our energy equation, which is a little bit more in depth. So D, the change in temperature of the change in time, is equal to, again, Q divided by V, or flow rate divided by volume, times the temperature in minus the temperature, plus, and this is going to be a big one, plus HR times K times CA times our rate constant times our concentration divided by rho, or density, times C, that heat constant, then minus UA times divided by rho, or density, times, I'm going to put another parentheses here, times our volume, times our heat constant. So all of that is our heat capacity. So good, and then multiplied by temperature minus the coolant temperature. Okay. If we shift enter, there shouldn't be any issues. All right. Now we're going to create a variable called sol for our solve IVP equation, and now we want, first and foremost, our function, we want RHS. We want a time span, which is going to be 0 to t end, some arbitrary time, y0, which is going to be our values. So we've got CA naught as well as T naught. Then we want our dense output to be true, and I almost forgot. Nope. Let me go this way. We need our method to equal. We want to use redo. There. Now we can use .sol for the variable name tend is not defined. Let's call tend 10, just 10 minutes. And we also need to put in our TC. It's going to be equal to 305. Because that's what's given in the thing, which I don't know. Come here, you. There we go. Which I'm going to pull over now. Anyways, so from 300 to 305. So we'll start with the 305. So now if I shift enter that, I'll shift enter everything just to run everything. That should work. Cool. So now we want a time plot is equal to numpy.linspace for linear spacing of 0 to t end with, say, 100 points. No, let's do 500, and then we're going to be using, nope, not that. So CA as well as T is going to be equal to, so our concentration, our temperature is going to be equal to running our sol function for t plot. For our plot, sol t plot. Shift enter. We have CA and T. Now we can create our plot. So that is fig is equal to make subplots here. We want fig.add, and we're actually going to be making sure rows equals 1, column equals 2. Now, if we add the scatter, we've got x equals fig dot. Nope. There. Now we've got x equals our time, so t plot. Y is going to be equal to, this could be either our concentration or the temperature, but it's going to be concentration. We want mode to equal lines, and we also want a name. Name equals CA. Now I just want to make sure that this runs. It does. That is good. I am happy about that. Now, if we add another one for x equals t plot again, y is equal to temperature, and then mode is equal to lines, name will be equal to temperature. If we shift enter that, forgot to put which row specifically. Row 1, col 1. Now if I put row equals 1, col equals 2, to specify what rows and columns. Good. Okay. That should be good. At the very least, that's a plot. I just want to make sure and look back and make sure that that's correct. I'm not sure that this looks right. Because this should, with a reaction and with inputs, go up and down like that. Let me check to make sure. I have all of this. Let me check to make sure that that looks right. Ooh. Aha, here. Oops. I accidentally, volume cancels out, but I accidentally put it there now. That looks better, yes. So as you can see, as this comes down to near 0, the reaction sum basically completes. And then again, because there's no nucleus for the reaction to start anymore, the concentration of A can grow, hit the breaking point here, then the reaction kicks off again. Then when there's not enough A of A to go to B, it grows, kicks off, stops, concentration grows, falls. And then the temperature, as the reaction keeps going, increases because it's an exothermic reaction, then drops as the coolant leaches heat off as well as the reaction stops, and goes up as the reaction goes, reaction ends, reaction starts, reaction ends, reaction starts. So that is our 305 degree idea. I'm going to put TC1 just to make things a little bit more interesting. Let's call it TC2 is equal to, and this one wanted what, 390 or 290? Yes, 290. 290 dot Kelvin. Okay. I am going to TC1. I'm going to copy and paste this as well. Control C, Control V, do TC2. Make sure that I get anywhere else. I'm going to again, let's do SO1. Nope. SO1. I can shift enter, shift enter, shift enter, shift enter, and good. Shouldn't change anything. Good. And then I'm going to simply copy. Oh, great, my mouse pad's acting out. Simply going to copy and paste this. Control C. Going to shift enter this. Run this. Run this. Whoops. Copy and paste again. I'm simply doing this process again for the lowering of the cooler. Oops, that is Control V. Undo insert. No, please, why? Can I undo that? Well, that's not right. Oh, time to rewrite this. We had Fig. We'll call it Fig 1 now because we're adding another figure. Is equal to add scatter rows equals 1, cols equals 2. Oop. Make subplots. There. Okay. Fig.add scatter x equals t plot y equals CA, mode equals lines, name equals CA, row equals 1, call equals 1, enter, nope. Good, enter, fig 1. Now I'm just going to copy and paste this. Stop that. Stop. There, okay. This will be temperature. This will be temperature. Shift enter should not change anything. It did. Call it 2. Shift enter. What changed now? Oops. There. Okay, now we're back. No, shift enter, shift enter. Going to copy and paste this. And copy and paste this. We'll call it fig 2. This will be sol 2. That should work. There. Now you see that there's a difference in the cooling and the running, and a difference in how it plays out. So the concentration of A goes up, it goes up, goes up, and almost never kicks off, and the temperature just keeps decreasing. All right, well, there you have it. Hope you have a wonderful day, and thank you very much for watching.